Right, we are on Chapter 14, page 4. We're going to be looking at ionic size. So we're going to be looking first at cations and then at anions. So let's start first with cations. Remember, cations are the ones that have the positive charge. You positively hate or like cats. So cations are always going to be smaller than the original atom. And let's take a look at why that is. We're going to compare magnesium to magnesium 2+. And let's first do the electron configuration for both of them. Magnesium is 1s2, 2s2, 2p6, 3s2. Now, if we're going to form magnesium 2+, that means two of these electrons are going to be lost. So magnesium 2+ will have the electron configuration of 1s2, 2s2, 2p6. Let's go ahead and draw the Bohr models for each of these. They're both going to have 12 protons in the nucleus. So let's go ahead and put those in. So 12 protons, 12 protons. Okay, let's put the principal energy levels around each nucleus. So we're going to have a total of 3 principal energy levels. Around neutral magnesium. Let's go ahead and put in the electrons. We'll have 2 electrons in the first energy level. We'll have a total of 8 in the second. And then we're going to have 2 in the valence shell. Now, if we lose 2 electrons, the 2 electrons that we're going to lose are these right here. So let's have these 2 electrons take a hike. Let's draw what happens after magnesium becomes magnesium 2+. We're going to have the first principal energy level, which is still going to have 2 electrons in it. And we're going to have the second principal energy level, which has 8 electrons in it. At this point, we have accounted for all the electrons. We no longer have a third principal energy level. Thus, the atomic radius for magnesium 2+ is going to be smaller than for the neutral atom. So cations are always smaller than the original atom. Makes sense. They've lost electrons. Anions are going to be just the opposite. They are always going to be larger than the original atom. And let's take a look at why this is so. We're going to first take a look at fluorine. The electron configuration for fluorine is 1s2, 2s2, 2p5. When it becomes an anion, it's going to pick up an extra electron. So it's going to become 1s2, 2s2, 2p6. Notice that this is what we call isoelectronic with neon. It now has the same number of electrons as neon. So let's start off by drawing our neutral atom of fluorine. It's going to have 9 protons in the nucleus, and it's going to have 2 principal energy levels. I'll try to remember to draw it smaller than magnesium up there. So there's our 2 principal energy levels. We have 2 electrons in the first shell and a total of 7 electrons in the second principal energy level. We're going to have a new electron come in. Meow. There it goes. It's coming in. So let's look what happens. We still have 9 protons in the nucleus. So the first principal energy level is staying the same size. We've got 2 electrons in that first principal energy level, feeling the pull of 9 protons. Now, we have added another electron to this second principal energy level, which makes this second principal energy level expand for 2 reasons. First, when we put another electron in here, electrons actually repel each other. So they're going to tend to expand to escape each other's repulsion. Now, when we add an electron, when we're adding protons, things balance each other out, but we're not adding any protons here. So we also are feeling less of an effective nuclear charge because these, to some extent, shield each other. So what we're seeing is the electron cloud is swelling because we have the same number of protons but a greater number of electrons. So what's going to happen anytime you form an anion is the anion is going to be larger than the original parent atom.